We are team number 2 and we will solve this for a couple of differential equations. First we have this one, y double prime plus 2y prime plus 5y equals to 0 with the initial conditions y of 0 equals 1 and y prime of 0 equals 2. So we easily can get the auxiliary equation lambda squared plus 2 lambda plus 5 equals 0. So to solve this and find the values of lambda, we use the general formula minus b plus minus the square root of b squared minus 4c over 2, because a will be always 1. So we have minus 2 plus minus square root of 4 minus 20 over 2. So we will have an imaginary number, which will be, we have here minus 2 plus minus square root of minus 1 by square root of 16 over 2. So we find that minus 1 plus minus 2i. So we use this case and we apply it to the formula. So we have y equals to e to the power of minus x by a sine of 2x plus b cosine of 2x. That will be our general solution. So now we have to evaluate it with the initial conditions. Y of 0 equals 1, so y of 0 equals 1, sine of 0 is 0, cosine of 0 is 1, so we found that b is 1. Now we derivate this solution and we find this e to the power of minus x by 2a cosine of 2x minus 2b sine of 2x minus e to the power of minus x by a sine of 2x plus b cosine of 2x. We evaluated y prime of 0 equals 2, so finally this is 1, this will be 0, the same here. So we find that 2 equals to 2a minus 1 because b it's 1. So a will be 1.5. So we finally get our particular solution, y equals to e to the power of minus x by 1.5 sine of 2x plus cosine of 2x. Now we have this differential equation, y triple prime plus 5y double prime plus 8y prime plus 4y equals to 0. We can get the auxiliary equation, lambda to the third power plus 5 by lambda to the second power plus 8 by lambda plus 4 equals to 0. So to get the values of lambda, we use the synthetic division. We try with a value of minus 2. We multiply, we have 3 by minus 2 minus 6, 2 minus 4, so we have at last 0. So it means minus 2, it's a value of lambda. So we get here 2, these 2, yeah. So lastly we have lambda plus 2 by lambda plus 1 by lambda plus 2 again. So using this case, we found that the general solution is y equals to c1 by e to the power of minus 2x plus c2 by x, for not repeating this, by e to the power of minus 2x again, plus c3 by e to the power of minus x. That's our general solution. we have this differential equation for y double prime equals x to by y prime to the second power. So we know y prime equals to z, and y double prime equals z prime. So if we substitute, we have 4z prime equals x by z to the second power. So we change this one, and we have 4 dz over dx equals x by c squared. To get rid of this, we integrate both parts. So we have minus 4 over c equals x to the second power over 2 plus c. So we then change this one by this dy over dx, and if we change this, we finally got minus 4 dx over dy equals x squared over 2 plus c. Then we change this to be minus 4 dx over x squared plus 2c over 2, so equals dy. And finally we got minus 8 dx over x squared plus c equals dy. We integrate both parts, and we have our general solution, which is y equals to minus 8 over square root of c, inverse tangent of x over square root of c plus c2. So at last we have this differential equation, y prime square equals 1 over 2 y by y double prime. With the initial conditions, y of 0 equals minus 1 and y prime of 0 equals 1. So we know that y prime equals z and y double prime equals z by dz over dy. So we substitute, and we have c squared equals yc dc over dy all over 2. So we pass this to the other side. 2c squared equals yc dc all over dy. Then we have 2z squared dy equals y c dc. And lastly we have 2 dy over y equals dc over z. We integrate both parts, and we have this 2 natural logarithm of y equals natural logarithm of c plus natural logarithm of c. We use the rules of natural logarithms. So we have natural logarithm of y squared equals natural logarithm of c by c. We apply this e to cancel these natural logarithms. So we have y squared equals c by c. So we also know c equals dy over dx. So we substitute this, and we have y squared equals dy over dx by c, our constant. After that we have we change this to the other side, and we get together the y's. So we have dx equals dy by c over y squared. We integrate both parts, and we have x equals minus c1 over y minus c2. So we change everything to find the y value. So we know y equals minus c1 over x plus c2, and that's our general solution. But we also have to find the particular solution with the initial conditions. So we know y of 0 equals minus 1, which is minus 1 equals minus c1 over x plus c2. We find out c1 equals c2. Now we derivate this, so we know y prime equals c1 over x plus c2 all to the second power. So y prime of 0 equals 1, which is equal to c1 over x plus c2 squared. Because x is 0, we have 1 equals to c1 over c1 squared, because we know c1 equals to c2, so to have the same values, we use the same c1. We know 1 equals to 1 over c1, so c1 its value is 1, the same as the value of c2. And finally we have y equals to minus 1 over x plus 1. That's our particular solution.